Okay everybody, welcome to the last video that's going to introduce some new content, and that new content is going to be on catalysis. So we all know what a catalyst does. It speeds up the reaction, but maybe we don't know exactly how it does that. Well, here I've got a free energy reaction coordinate diagram that shows some hypothetical reaction. Now take a look at my diagram. How many elementary steps does it contain? Well, I've got one hill, two hills, so I've got one hill for each elementary step, so I've got two elementary steps in this reaction. Which step is slow? Well, the second step is slow because it's the bigger of the two hills. So the second step is the one that contains the activation energy for this reaction, and that activation energy is going to be about that tall there. Okay, there's the activation energy. So what a catalyst does is it fundamentally changes the reaction in such a way as to lower the activation energy. Now, a catalyst doesn't just simply let the same things happen but faster. What it does is it actually tweaks the mechanism a little bit so that the activation energy will be a little bit lower. So, for example, I might introduce a catalyst in this reaction, and I'm going to go ahead and make the catalyzed reaction green here. And what it does is, maybe it doesn't mess with the first step too much, but it's going to alter the second step so that its activation energy is some energy less than what it took to do the uncatalyzed reaction. So in a way, what I have up here between the two heights of the two tallest hills is I have a change, a delta, in the activation energy. Now, the details of how the activation energy gets lowered is not going to be our concern for any particular reaction mechanism, but that's the net effect. Now, notice this is different than temperature. What temperature does is temperature allows more molecules to get over the activation energy barrier. It doesn't change the activation energy for a reaction, altering temperature. Only adding a catalyst will actually alter the value of the activation energy. Now, let's take a closer look at some of the implications of this mathematically. I'm just going to move this guy out of our way for now. You remember the equation we had from Arrhenius, the Arrhenius equation, where the natural log of K is equal to negative EA over RT, sorry, this isn't very neat, over RT plus ln of A. Now, I could actually apply the Arrhenius equation to my reaction system. So I'm going to write this equation again. ln K is equal to negative EA over RT plus ln A. So I could have the activation energy for the uncatalyzed reaction that I'll represent as a U. That will have some rate constant, K sub U. And then I could have the activation energy of the catalyzed reaction, I'll call that E super C, with a rate constant, K sub C. And so I could then go ahead and combine these equations, not unlike what we did for the temperature variation, and arrive at a conclusion that looks something like this. The ln of K catalyzed over ln of the K uncatalyzed is equal to the difference in the activation energies over RT. You see that the natural logs of A get factored out. So this is a handy little equation for us to evaluate quantitatively the impact of putting in a catalyst. So if I put in a catalyst, maybe I get a 100-fold change in my reaction rate. Well, what did that do then to the activation energy? You'll find out that when you have, say, a 10-fold increase in the reaction rate, the activation energy doesn't get changed by all that much at typical temperatures. All right, we're only talking about small deltas in the activation energy. All right, so let's take a look at a catalyst in action. I'm going to write a reaction that involves a catalyst. And the reaction we're going to talk about has to deal with ozone. In the upper atmosphere, we can actually see the reaction of atomic oxygen plus ozone to give 2 molecules of molecular oxygen. This is going on in the upper atmosphere as we speak. And this is related to ozone destruction, right? Back in the 70s and 80s, there was a pretty big hole in the ozone layer, which causes us problems in terms of ultraviolet radiation. And over the years, you know, it's shrunk and it's gotten bigger, it's shrunk and it's gotten bigger. But we did learn in the very early 80s that one of the contributing causes to the expansion of the hole in the ozone layer was the use of CFCs, chlorofluorocarbons. Because it turns out the chlorine in chlorofluorocarbons can actually accelerate the decomposition of ozone by this reaction. So here's what the catalyzed reaction looks like. It involves atomic chlorine reacting with the ozone to give us, I want to make sure I'm writing down the reaction correctly here, ClO plus O2. And then what happens in a second step is we get the atomic oxygen to react with that ClO to produce Cl plus O2. So as you can see in this reaction, it involves a couple of things. ClO, hopefully you recognize what that is. Can you tell what ClO is doing in this reaction? ClO is an intermediate. It is the product of an early elementary step and a reactant in a later elementary step. So it's not there, it shows up, it goes away. That's an intermediate. Meanwhile, chlorine here is the catalyst. It's there at the beginning, it goes and does its thing, and it comes out the same at the end, right? That's what a catalyst can do. And so then, once this chlorine gets to here, it can then go back in and do it all over again. So one chlorine atom can actually accelerate the reaction of the destruction of ozone several times over. That's what a catalyst does. It turns over and over and over and over again. Okay? So this is an example of a catalytic process I guess we would prefer not to have happen, but there it is going on in the upper atmosphere. And so somehow, in this we won't get into the details, but somehow the addition of chlorine here ends up effectively lowering the activation energy, like I showed in that general reaction coordinate diagram. And we can quantify all of this process by doing a variation on the Arrhenius equation. All right, that's it. That's everything for new material. Maybe we'll do a quick little review video, but that's all for now.